Hi everyone, in this video I will be going through the week 16 PARTE packet questions. So getting right into it, question 1 asks, of the following compounds, which below forms an atomic crystalline solid? And we want to select all that apply. So probably the easiest way to do these types of problems is to draw the structures if you know what they look like. So we'll do that for each of these molecules here. So oxygen, 2 double bonded oxygens, methane, a carbon single bonded to 4 hydrogens. Helium is just a single monatomic helium atom. Same with xenon and radon. The helium, xenon, and radon are all noble gases, so they don't form compounds very readily, so they're monoatomic. And then carbon dioxide is a carbon double bonded to 2 oxygens. So here we're looking for atomic crystalline solids, so those are going to be single atoms. So in that case, that is going to be xenon, radon, and helium, because oxygen, methane, and carbon dioxide all form molecules where we're looking for single atom crystalline solids. So again, xenon, radon, and helium is the answer for number 1. Moving to number 2, of the following compounds below, which form molecular crystalline solids? And again, we want to select all that apply. So again, for each of these, we'll draw what each of these compounds look like. So diamond is going to form kind of a lattice of carbons, with each of the carbons bonded to 4 other carbons. Quartz is similar, so I'll draw that down here, where it's going to be a network of silicons and oxygens. Something like that. Oxygen, as we drew in the previous question, 2 double bonded oxygens to each other. Methane, carbon single bonded to 4 hydrogens. Sodium chloride is a sodium cation and a chloride anion. And then carbon dioxide is a carbon with 2 double bonded oxygens. So here we're looking for molecular crystalline solids. So that is going to be methane, oxygen, and carbon dioxide. Here, although these have covalent bonds, these are going to be different types of solids where it doesn't have the extended pattern. So things like oxygen and methane and carbon dioxide, those individual molecules come together when they form their crystals. And then sodium chloride has a sodium and chloride ions, so those are going to be a different type of solid. So oxygen, methane, and carbon dioxide all form molecular crystalline solids. Moving to number 3, of the compounds below, which form ionic crystalline solids. So we'll draw each of these. So lithium fluoride, lithium cation, fluoride anion, carbon dioxide, we'll draw that again. We've seen xenon, we've seen diamond, so I'll just draw a somewhat smaller lattice for that one. Calcium oxide is calcium 2 plus cation and oxide 2 minus anion. And then sodium chloride, sodium cation, chloride anion. So here we're looking for ionic crystalline solids, so that is going to be anything where there's an ionic bond between the atoms involved. So that is lithium fluoride, calcium oxide, and sodium chloride. Those are going to be the ionic crystalline solids. As we've seen previously, carbon dioxide and xenon are different types of crystalline solids, and diamond, again, does not have ionic bonds, so these are going to be the 3 that form our ionic crystalline solids. Number 4, of the compounds below, which form network crystalline solids. So lithium fluoride, again, lithium cation, fluoride anion, methane, the carbon with 4 single bonded hydrogens. Quartz, I'll draw that down here. That's where we have the network of silicon and oxygen bonds, where then each of these would continue to additional silicons. That's quartz. Carbon dioxide we've seen several times now. Silicon and diamond are both really similar, so we've seen diamond a few times where we have the network of carbon-carbon bonds where each carbon is bonded to 4 other carbons. Silicon is the same thing. It's an analog of carbon. It's just one row down in the periodic table, so it's going to behave similarly to carbon. And in things like computer chips and stuff where they have silicon chips, they're going to have network silicon. So we're looking for network crystalline solids, and that's going to be anything where there's a repeating pattern for most of the solid. So things like diamond, silicon, and quartz all fall into the network crystalline solids because you have a network of repeating units that is all interconnected through covalent bonds, like we see here. Moving to number 5, it says glass is an example of which type of crystalline solid. So there's a couple that we can rule out here immediately. Globular and fibrous, those are not types of crystalline solids. Those are both types of proteins. So we can rule those out immediately. Then we need to look at single crystal, polycrystalline, and amorphous. So a single crystal is just what it sounds like. You have a single crystal lattice that just has a repeating pattern. Something kind of like this, where there's no non-uniformity. It's just a repeating pattern that is continuous throughout the material. Polycrystalline is where you have a grouping of many little crystals. So you might have one like that. You might have a second crystal there. You might have a third crystal like that. So there's several individual crystals. Something like granite falls into this type of a category, where there's crystals maybe even of different materials connected near each other, but not one uniform crystal. And then amorphous is where you have kind of a random disbursement of the atoms in the structure. You may have some very small areas of regularity, but for the most part, the molecules or atoms involved in a amorphous crystalline solid are going to be pretty randomly distributed, and glass is going to be an example of the amorphous crystalline solid. The silicon dioxide atoms and molecules within the glass is going to be distributed randomly with no either groupings of crystals or long order regular structure like we would see in the single crystal or the polycrystalline materials. So glass is going to be an amorphous crystalline solid. All right, moving to number 6. Says which of the highlighted areas below represent unit cells. So we want to select all that apply here. So a unit cell is something that can be translated along its axes, and you'll have the exact same area enclosed, either translating along the x or y axis. So if we look at A here, if we translate that to the right, you will still have the same area enclosed, but if you translate it in the other direction, you now have half black, full white cell, and then another half black cell, whereas the original was half white, full black, half white. So A is going to be out because we don't get an identical representation when we translate along this axis of the unit cell. Same for B. If we translate it up 1 unit, we have this full black cell in the middle. Now we would have a full white cell with a half diagonal black cell on each side, whereas before it was a half diagonal white cell. So that is not the same when we translate it along the y-axis here. So B is also out. If we move to C, we have 4 squares, white, black, black, white. If we translate that 1 unit over, so that would be right here, we do see we have the same pattern. So if this was now our unit cell, we have the white, black, black, white pattern that we saw here. So white, black, black, white. And the same if we go up along its other axis. Now we're here. That's going to be again white, black, black, white. Just what we saw in the original was white, black, black, white. So C is a unit cell. If we look at D, if we go up, we have a white, black cell. If we go to this unit cell, translating in the X or the y-axis again, we have black, white. So in that direction, it is all right. But if we look in the other direction, the x-axis, we now have a white on top of a black cell, which is not a duplication of what our original was. So D is not a unit cell. And then moving to the last one, E, we have a quarter black, half white, quarter black, half white, repeating around with a black cell in the middle. If we move that up in the y-axis, we see that we have the same thing duplicated there. Quarter black, half white, quarter black, half white, all the way around with the black in the middle. And if we translate it in the x-axis, again we see that we have the same thing. Quarter black, half white, quarter black, half white, around a central black cell. So E is also a unit cell. So C and D, when you translate them in the x and y-axis, you do get an identical replication of what the original cell contained, whereas you do not with A, B, and D. So C and E here are going to be unit cells, whereas A, B, and D do not represent unit cells. Moving to number 7, it asks how many marbles are in each of the unit cells seen below. So we have 5 groups of marbles here with various shaped unit cells surrounding the marbles. So if we look at each of these, here we have quarter marbles within the cell. So there's 4 quarter marbles, one for each of the 4 marbles that are partially within the unit cell, and there are 4 of those. So there's 4 quarters there, so that is equal to 1. There's 1 marble in that first unit cell. We'll do a similar thing for the second one here. So again, there's 4 quarter marbles, 1 in each corner. There are 4 half marbles, 1 along each of the sides. And there's 1 marble in the middle, so there's 1 of those. So quarter times 4 is 1, half times 4 is 2, and 1 times 1 is 1. So in that cell, there are going to be 4 marbles. Here we see a diamond around a central marble, so there's 1 marble in the middle. That's 1 whole marble, that's 1. And then again we have a quarter marble on each corner. So there's 4 corners, so each quarter will equal 1 total. So in this cell there are 2 marbles. In this hexagon unit cell, there's again a central marble. And now we have kind of an irregular angle here, so that's 1/3 of a marble. And there are 6 corners on our hexagon, so that's going to be 1/3 times 6. That is equal to 2. And 1 times 1 is 1, so there are 3 marbles in this hexagon unit cell. Then if we look at this diamond here, we have 2 different sections of marble. We have the little section in the bigger section. So the little section is actually 1/6 of a marble, and the bigger section is 1/3 or 2/6. So there's 2 of each. So here that's 2/6, and here that's 4/6. So 2 plus 4 over 6 is 1. So in this final cell, there's going to be 1 marble there. Moving to number 8, which of the crystal structures below has the greatest packing efficiency? So this is something you can get kind of a qualitative number just based on looking at each of these. This one looks like it might be packed less than this one, and this one looks like it has the most compact structure of these 3. You can remember that each of these has a number associated with it for packing efficiency. So for the simple cubic, that's got about 52% efficiency. For the body-centered cubic, that's about 68%. And then for the face-centered cubic, that's about 74% efficiency. But if you wanted to know how we get each of those numbers, we can treat the atoms here as having a radius of 1. So we'll set r equal to 1. We'll start with the simple cubic here. So in order to find the volume taken up by the spheres within this unit cell, we need to take the volume of the spheres and divide that by the volume of the cube. So if we first find the volume of the cube, in this case it's easy. There's 2 radiuses along each edge, so that's going to be 2 times 2 times 2. So there our volume for the cube is going to be 8. That'll be our denominator. And then to find the volume of one of these spheres, so remember for the simple cubic, there's 1 complete atom in the unit cell. In the body-centered cubic, there's 1 on each corner, so that's 1 and then 1 in the center. So there's 2 atoms in the body-centered cubic, and then there are 4 atoms in the face-centered cubic, a half along each face for a total of 3, and then an 1/8 at each corner for an extra 1, so that is 4 atoms there. So we need to find the volume of one of these spheres. For that we need to know the formula for the volume of a sphere. So that is 3/4 pi times r cubed. Here r is just 1, so it's going to be 3/4 pi, and that is approximately equal to 4.189. So if we take that as our numerator, we have 4.189 divided by 8. That is going to equal approximately 0.52 or 52%. So we can do something similar for the other 2, the body-centered cubic. So here we don't know what this side is because there's a small gap in here. So we need to figure out what the length of this side is. Again, we'll set the radius of the atom inside as 1 just to make it simple. And then we do know that if you go from this corner to this corner, that's going to be 4r. So we can find the length of this side A here. We'll label this B. And then along this diagonal, we'll label that C. And then from opposite corners of the cube, we'll label that D. So we know that D is equal to 4 radii because you have a 1/8 atom in the corner on each side and a full atom in the middle. So across that long diagonal, you're going to have 4 radii. So we want to solve for A in this case, given that we know that D is 4R. So using the Pythagorean theorem, D squared, which is the hypotenuse, is going to be equal to A squared plus C squared. So this, again, being a cube, this is also A. So A squared plus C squared is equal to D squared. But we also don't know what C squared is in this case. So C squared is going to be equal to A squared plus B squared. Since these sides of the cube are the same, C squared is going to be equal to 2A squared. So if we plug in what C squared is equal to in this formula here, that gives us D squared is equal to A squared plus 2A squared, or D squared is equal to 3A squared. So if we take the square root of both sides here, it's going to give us that D is equal to the square root of 3 times A. We know that D is equal to 4R. So 4R is equal to the square root of 3 times A. So A is equal to 4R divided by the square root of 3. So again, R is equal to 1 in our example here. So A is equal to 4 over the square root of 3, which is approximately equal to 2.31. If you take 4 divided by the square root of 3, it's 2.31. So we have A, if we take 2.31 times 2.31 times 2.31, that is going to give us the volume of the cube, approximately 12.32. So that's going to be our denominator here. We want the volume of the spheres over the volume of the cube. So here, as I said, there are two spheres. If we use the same area for each sphere, because again the radius is still equal to 1, that'll be 4.189 times 2. So that is going to be 8.378 divided by 12.32, and that's going to be approximately equal to 0.68, or 68% packing efficiency for the body-centered cubic. Then if we look at our final example, the face-centered cubic, here we can see that along this diagonal, so we have A, B, and C. C is going to be equal to 4 radii, so you have one here, 2 for the full circle, and another one here for the corner. So that's C, that's equal to 4R. And then using the Pythagorean theorem again, C squared is equal to A squared plus B squared, where A and B are the same. So C squared is going to be equal to 2A squared. And then if we take the square root of each of those sides, it's going to be C is equal to root 2 times A. So we know that C is equal to 4R. So 4R is equal to the square root of 2 times A. So A is equal to 4R over the square root of 2, where R, again, we're keeping as just equal to 1 to make our calculation simpler. So there it's going to be 4 over the square root of 2, and that is equal to 2.828. So that is A. So if we take 2.828 times 2.828 times 2.828, that's going to give us the volume of the cube, and that is going to be 22.62 approximately. So then again, we'll use the volume of our circle, or the sphere that we've calculated, 4.189. Now there's 4 spheres in the face-centered cubic, so we'll multiply that times 4. That's going to give us 16.756. We'll divide that by the volume of our cube, 22.62, and that's going to give us approximately 0.74, or 74%. So if we look at our answer choices here, which has the greatest packing efficiency, 3 has the greatest packing efficiency, as we just calculated, so that is going to be C here. It has greater than 2 and 1, so the face-centered cubic has the greatest packing efficiency. Moving to problem number 9. It says an element crystallizes in a body-centered cubic lattice and has a density of 0.86200 grams per cubic centimeter. The edge of its unit cell is 532.08 picometers. So there's a couple different parts to this question. So the first is how many atoms are in each unit cell. So here it says that it's a body-centered cubic unit cell. From the previous problem, we said that there were 2 atoms in each of the body-centered cubic unit cells, so A is 2 atoms. We also need to calculate the radius of the atom in picometers, so we're given its edge length. So using the information that we had in our previous problem, or we can look at our handy helpful information sheet here for the body-centered cubic, where we see that A is equal to 4r over the square root of 3, which is what we calculated in the previous problem. So here we have that A, which is the edge of the unit cell, is equal to 532.08 picometers. A is also 4r over the square root of 3. So if we set those equal to each other, it's going to be 532.08 picometers is equal to 4r over the square root of 3. So if we multiply 532.08 picometers times the square root of 3 and then divide that by 4, that is going to give us r, or the radius of the atom, and that is going to be equal to 230.40 approximately picometers. So for B, so 0.40 is just an approximate. The full number is 0.39739 picometers, and not rounding will help with in our subsequent calculations here. So C asks what is the volume of a unit cell in cubic centimeters. So here we have the edge length of the unit cell already in picometers, so we just need to take the cube of this number after we convert to centimeters, and that'll give us the volume in cubic centimeters. So we have 532.08 picometers. We'll multiply times the conversion factor. So 1 centimeter is equal to 1 times 10 to the 10th picometers. So the picometers will cancel, and that will give us 5.3208 times 10 to the negative 8th centimeters. So now to find the volume of the cube, we know the length of the edge of the unit cell in centimeters. 5.3208 times 10 to the negative 8th. We'll take that to the 3rd power. and that will be equal to 1.506367 times 10 to the negative 22nd cubic centimeters. So we'll add that here. So that was part C. Part D asks, what is the volume of 1 mole of the element in 1 cubic centimeter? So for that problem, I'll get a new page here. So we want to know the volume of 1 mole of the element in cubic centimeters. We know how much 1 cubic centimeter is. So if we have 1.506367 times 10 to the negative 22nd cubic centimeters, and that is for 1 unit cell. Well, we're going to multiply times Avogadro's number. So that is 6.000221409 times 10 to the 23rd, and that's atoms per mole. So if we multiply those two numbers together, that is 90.71554, and none of these units cancel, so that's cubic centimeters times atoms over unit cells times moles. So that is for the volume times atoms over the unit cells times moles. There isn't just a single atom in this unit cell. So if we want to cancel the atoms and unit cells, because we want to know cubic centimeters per mole, we'll need something that has those units. So unit cell over atoms. So in 1 unit cell for the body-centered cubic, there are 2 atoms, so we're going to divide this number by 2. That'll cancel those 2 units, and that'll give us 45.3577 cubic centimeters per mole. So that is for part D, 45.3577 cubic centimeters per mole. Moving to part E here. What is the mass of a unit cell in grams? So we know the volume of a unit cell that we calculated in part C, and we know the density of the unit cell. So if we multiply the volume, which is 1.506367 times 10 to the negative 22nd cubic centimeters, we're going to multiply that times the density, which is 0.862 grams per cubic centimeter. The cubic centimeters are going to cancel, and that'll give us the mass in grams, which is 1.29848 times 10 to the negative 22nd grams. So we'll add that for part E. Then we want to calculate an approximate atomic mass for the element in AMUs per atom. So in order to do that, we are going to use the mass of our unit cell in grams, 1.29848 times 10 to the negative 22nd grams. We're first going to convert to kilograms and then to AMU. So to convert to kilograms, we'll multiply times the conversion factor, which is 1 kilogram over 1,000 grams, so basically just dividing this number by 1,000. That's going to give us 1.29848 times 10 to the negative 25th kilograms. So if we multiply that number times 10 to the negative 25th kilograms times the conversion factor for AMU, which you can get from the useful information sheet, that is going to be multiplied times 1 AMU over 1.66054 times 10 to the negative 27th kilograms. So there, the kilograms will cancel, and that will give us a value of 78.19675 AMU. And remember, that's going to be for the entire unit cell, because this was the mass of the unit cell. So that's what we calculated in E. So that's per unit cell there. So here, this is also going to be per unit cell. Remember, since this is a body-centered cubic, there's going to be 2 atoms there. So if we want to cancel the unit cell's unit here, we'll multiply times something that cancels that. So here we have unit cells on top, and we're figuring out how many atoms are in the unit cell. So one unit cell has 2 atoms, so unit cells will cancel there, because we want to know AMUs per atom. So that's what we want our final units to be, is AMUs over atoms. So if we divide 78.19675 by 2, that will give us 39.09837 AMU. So that is for F, 39, let's say, 0.1 AMU, if we round this number up. So then D or G is identify the element. So if we look at our periodic table here, we're looking for an element that has an atomic mass of 39.1. So if we look here at calcium, that's the atomic mass there, 39.1 AMU. So the element in this problem is potassium. Alright, moving to problem number 10. It says, in the image of a crystal lattice below, what type of structural defect is not present? So we have a list of potential structural defects that we need to look for here. So we'll just go through those one by one. A is a substitution. That's where one of the main atoms of the lattice is going to be replaced by another atom. We see that most of these are gray circles, but here where there should be a gray circle, there's actually a blue circle. So that is a substitution. So we do have a substitution. A vacancy is where there's a missing atom where there should be one. So we see that here, if the lattice were complete, there would be another gray circle there. So there is a vacancy because we're missing a gray circle here. An interstitial atom is where there's another smaller atom placed in between the main circles of the lattice, so the main atoms. So here, this red circle represents an interstitial atom. It's in between the main lattice composed of these gray atoms here. So there is an interstitial atom. An edge dislocation is where one of the edges of the lattice has been displaced from what it normally would be. So if we look at the bottom row here, we can see that the centers of each of those gray circles representing the atom line up. But if we look along here, along these 3 atoms, they do line up, but they don't line up with the rest of the lattice over here, whereas these three line up, but they don't line up with the rest of the lattice over here. That means that there's been an edge dislocation along this axis, because all of these atoms along the x-axis here, those all line up. If you go up through the rows here, all of those line up. So that means that the edge dislocation has happened along this axis. This upper portion has slid over, or the bottom portion has slid a little bit relative to the rest of the lattice, so there is an edge dislocation, so that would have to mean the answer is E. All of the structural defects are present in the representation of this lattice that we see here. Number 11. Crystal lattices containing two different ions are made of cations and anions. Which type of ion usually forms the lattice, and which type of ion usually fills the holes of the lattice? So the lattice is going to be the main atoms that you see on the corners. So the atoms that go here, for example, in a simple cubic, and then the holes are going to be in between those atoms. So we want to know whether cations or anions are the lattice or the holes. So if you think about a cation, cations are going to be positively charged, so that means that they're going to be smaller. When you have less electrons held by the same number of protons, that's going to shrink the atom or the ion relative to the neutral atom. And then if you have your anion that's negatively charged, that's going to go the opposite way. It's going to become larger than the neutral atom because the same number of protons is now trying to hold on to a larger number of electrons. That's going to increase the size. So the larger anions are going to be what are at the corners forming the lattice. And it would make sense that these smaller ions, or here the cations, those are going to fill the holes. So we want cations in the holes, anions on the lattice. So here that is B, anions form the lattice, and cations fill the holes. So this is what you're going to most typically see in all the cases that you'll run across here. Anions form the lattice and cations filling the holes. Moving to number 12, below is an image of a cesium chloride lattice. There's a couple different parts to the problem here. What type of lattice is formed by the chloride ions, shown in green? So here on each of the corners is a chloride ion. That is going to be a simple cubic. There's one ion on each of the 8 corners of the cube. That, as we know, is a simple cubic. So then B, what type of hole do the cesium ions fill? So that's going to be in the middle here. So each of these 8, and then one behind, there's 8 atoms. They're all touching the central cesium atom, so 8 chlorines are touching the central cesium. That is going to mean that the hole is a cubic hole because the coordination number for cesium is 8. So each of the 8 chlorines are all touching the central cesium. So there's 8 as the coordination number for cesium. And if the central cesium has a coordination number of 8, then the hole is going to be a cubic hole. If we look at number 13, now is the image of the zinc sulfide lattice. So same questions. What type of lattice is formed by the sulfur ions, shown in yellow? So here we see that we have a sulfur on each face as well as in each corner. That, as we know, is the face-centered cubic. There's an ion on each face, so therefore it's the face-centered cubic. Now we're looking at what type of holes the zinc ions fill. We can look at that similar to how we approached the previous problem. How many of the sulfurs are each touching the zinc? So if we look at this zinc atom that's in there, it's touching 1, 2, 3, 4 sulfur atoms. So 2 on these two faces, the third one in the corner, and the fourth on the lower face directly behind the zinc. So the coordination number there is going to be 4 for zinc, and when you have a coordination number of 4, that means you have a tetrahedral hole. So if you think about a tetrahedron, there's 4 sides to the tetrahedron. Each one of those faces is going to touch the zinc. So the coordination number there is 4 inside the tetrahedral hole, and then the sulfur ions are forming the face-centered cubic lattice. So 14, again, same question. Now for the sodium chloride lattice, what type of lattice is formed by the chlorine ions, shown in green here? So here again we see that there's 1 on each face, 1 in each corner. So this is also a face-centered cubic. But now the sodium ions are not in the tetrahedral holes like we saw in the previous zinc sulfide example. They're now in between each of the chlorines on each of the edges here. So that means that each of the sodiums is going to be interacting with 6 of the chlorine ions, and when you have a 6 coordination number for the anion, that means that the anion is, or the cation is then in an octahedral hole. So again, here is the sodium cation here. If you drew the rest of the lattice, there'd be another one here and another one here. So you have the 1 back there, 2, 3, 4, 5, 6. So the coordination number is 6. And then again, if you have an octahedron, something like that, then that is when you have a coordination number of 6 and you have an octahedral hole. So moving now to number 15, which hole type can accommodate the smallest cations? So there's a few of these we can rule out. We haven't talked about dodecahedral or icosahedral holes. We've only talked about tetrahedral, cubic, and octahedral. So there it's basically going to be the greater the number of sides, the larger the hole is going to be. So an octahedron is going to be 2 4-sided pyramids stacked on top of each other. So there's going to be 8 sides. A cube has 6 sides, and a tetrahedron is going to have 4 sides. So as I said, the greater the number of sides, the larger the hole. So the smaller the hole is going to be corresponding to the less number of sides. So their tetrahedral hole is going to accommodate the smallest cations, whereas an octahedral hole would accommodate the largest cations. Number 16, what is the empirical formula of the mineral whose lattice is shown below? So here red represents oxygen, blue represents calcium, and black represents titanium. So for the red, blue, and black, we have a red half on each face here. So half of a red, there's 6 faces. So 1/2 times 6 is equal to 3. For the blues, we have an 1/8 on each of the 8 corners. 1/8 times 1/8 is equal to 1. And then we have a complete titanium atom in the middle of the lattice, so 1 times 1 is equal to 1. So here the empirical formula is going to be 1 calcium, 1 titanium, and 3 oxygens, because remember red represents oxygen, blue represents calcium, and black represents titanium. Number 17, the final problem. A yellow LED is made of the semiconductor gallium phosphide, which has a band gap of 2.15 electron volts. What wavelength of light is emitted by the LED in nanometers? So here we're going to need this equation, which you can get from the useful information sheet. So that is the energy is equal to 1240 electron volt nanometers over lambda. So here we know the band gap in electron volts. We want to solve for the wavelength of light. So we'll multiply E times lambda and divide this by E. So that will effectively reverse the two. So the band gap is E here in electron volts. So that's 1,240 electron volts times nanometers over 2.15 electron volt band gap. If we divide 1,240 electron volt nanometers by 2.15, we get that lambda is equal to 576.7 nanometers. So that is the final problem, and that was the week 16 PARTE packet explanation.